about this chapter is memorizing what all of the different centers mean. So, I'm assuming that you have only dealt with 2 of them.
I've dealt with circumcenter, and I don't know about incenter.
Well, in the book, that's the first 2 they deal with. And I like it because rather than having to deal with all 4 types, if you start with dealing with these 2 types, it makes it far easier to remember. Remember what an incenter is. Remember we're talking about triangles. And remember that an inscribed circle would be a circle inside the triangle. A circumscribed circle would be outside the triangle. So if we're talking about inscribed, what is necessary for that to happen? We need to be equidistant from the 3 sides. In other words, that distance needs to be equal to that distance, needs to be equal to that distance.
You have to bisect all.
Well, here's the thing. Here's the way to memorize it. If we need to be equidistant from the 3 sides, then we need to start the process from the vertices. And the way you accomplish this is by bisecting each vertex. In other words, if I take a triangle and I start at the vertex and I bisect it, and I do that around, you know what bisecting the angle means, you get a intersection of the 3 lines. And that intersection ends up being equidistant when measured perpendicularly to all 3 sides. And the fact that all 3 of these dotted lines are equal, well, that's perfect for inscribing a circle. Because the radius, all radiuses of a circle are the same. So, the way to memorize what incenter is to start from the back, knowing that you're going to end up with a circle inscribed in a triangle. And the way you get that is not by starting from the sides, but by starting from the vertexes.
All right.
Now, circumcenter. How would you get a triangle whose center would allow you to circumscribe a circle about that triangle?
Equidistant from the vertices?
Exactly. In other words, these 3 lines have to be equal. And you get equidistant from the vertices by starting from the sides. In other words, for these 2, you always start from the opposite of what you're trying to end up with. In other words, if the way I create a circumcenter is to start from the sides of the triangle, you start from the midpoint of each side and you draw a perpendicular line. Start from the midpoint of that side, draw a perpendicular line. Start from the midpoint of that side, draw a perpendicular line. This center is equidistant from the vertices. In other words, to get a center that's equidistant from the vertices, we start from the sides. To get a center that's equidistant from the sides, we start from the vertices.
All right.
And to me, that's an automatic way of memorizing the difference between incenter and circumcenter, is to start from the back. You're going to get an incenter whenever the center of the circle is equidistant from the sides. It's the only way you can get an inscribed circle inside the triangle. And the only way you can circumscribe a circle is if the center is equidistant from the vertexes. And that being the case, we need to start from the sides. In other words, you either start from the sides or the vertexes. And you pretty much do the opposite for both of these. And once you remember it like that, then you should never really have any problem, again, with memorizing it.
Okay.
Now, have you gone further than these two, or have you only talked about these two?
This almost seems a little bit different because what we're kind of working right now is like ratios between two shapes and stuff like that.
Well, ratios between shapes.
So like the ratio of a...
Well, it sounds like maybe you have talked about medians or orthocenters.
I think we talked about orthocenters.
Okay, let's talk about that. In other words, if I take a triangle, this time I'm going to do a combination of the first two. I'm going to start from the vertex, and instead of bisecting that angle, I'm going to go to the midpoint of the opposite side. Notice that that's almost an exact combination of the first two methods. The first two methods, I either bisected this angle from the vertex, or I started from the midpoint of the other side and went perpendicular. Well, this is a combination. In other words, if I go from here, this is called a median, to the middle of the other side, and I do that with all three vertices, oddly enough, they also intersect. And this is called the orthocenter.
So you have to do all three medians?
Hold on. I hope I'm not mixing these up. This is not the centroid, is it? This might be the centroid.
I think that's the centroid.
This is the centroid. And the centroid is has some very interesting properties. To me, this really is the center of a triangle. And the reason is if you had a piece of cardboard that was uniform in thickness, and you were trying to balance it on top of a pencil, you would want the centroid. The centroid is also the center of mass. And the centroid is the one that has the ratios, like you're talking about.
All right.
Whoops, hold on.
One of the ratios we were doing is like, if you have we were like doing a three-dimensional shapes, like you have to find the ratio of the volumes, the ratio of the area, surface area.
That's completely different. I'm not sure what you guys are doing there. Let me just finish this train of thought, and then let's go there, because maybe you're not on chapter 5. If you have a centroid, or center of mass of a triangle, then the distance AO is equal to 2/3 of AD. And this is the first one where we can make those kind of statements. In other words, with incenter and circumcenter, you couldn't say that. You could just say that it was equidistant from either the vertices or the edges. But this one, very specifically, is the long part of that is 2/3 of the total length. So CO is also equal to 2/3 of CE. In other words, every long line is 2/3 of the total line. And I guess one way I keep track of what centroid means is I know that centroid is center of mass, and therefore it has to be inside the triangle. And there's only one other kind of incenter, and that's the center that you get from drawing altitudes. Okay, let's talk about that again. If I have an obtuse triangle, if you want the orthocenter, you start from the vertex and you draw an altitude. Start from this vertex, draw an altitude. Well, I can see that the only possible place these two things can intersect is outside the triangle. If I start from this vertex and draw an altitude to the other side, I get that. That is the orthocenter. And the main difference with orthocenter is it's the only one that can be outside the triangle. The incenter, the circumcenter, and the centroid all have to be inside the triangle, but not the orthocenter. Do you see how I got this orthocenter? You see what I did? In other words, in order to get it, you kind of have to extend some of the lines. I really had to extend that line in order to draw a vertical to it. And I had to extend this line in order to draw a vertical to it. And I had to go backwards on this one so that all 3 points intersect there. But you start from the vertex and draw a perpendicular to the opposite side. And I don't believe that orthocenters have any special properties. Hold on. No. The centroid has, no. The altitudes, the only thing you can say about the altitudes is that they intersect. And they don't always intersect outside of a triangle. In other words, if I have a typical looking triangle and I draw a perpendicular to the opposite side, go to that vertex, draw a perpendicular to the opposite side, go to that vertex, draw a perpendicular to the opposite side, that orthocenter is inside the triangle. And it doesn't have any particular properties. You can't inscribe a circle or inside or outside. It's not the center of mass. So I'm not sure exactly what the orthocenters, the reason we even talk about it. But that's what it is. And it doesn't have to be inside the circle. So if you think of it as that, in other words, if you think of the special orthocenter that you have to draw an obtuse triangle to get it outside the circle, then it's kind of easy to distinguish from your other centers. This is a peculiar branch of geometry because once you're done with this chapter, you don't ever use it again. And I mean never. You don't need to know it for ACT test, SAT test, any kind of college geometry. So the only time you might use it is when you take a physics class. And they do refer to the center of mass, because that is actually a common problem. If I gave you a triangular sheet of cardboard and I said balance it on the end of a pencil, the spot would be the centroid. So centroid has all kinds of meaning. And I can see where end-center and circumcenter would also, because you can inscribe or circumscribe a circle about it. So those to me also would make sense as to talking about the center of a triangle. The orthocenter, not so much. I don't tend to think of the orthocenter as the center of a triangle, especially when it can be outside of a triangle. But the other three all have very legitimate reasons why somebody might call that the center of a triangle. The one that's the most logical to me would be the centroid. I mean, I would know, if my triangle was constant density, constant thickness, what would cause it to balance on the head of a pencil, and that's the centroid.
All right.
Now, in terms of the geometry problems that one can do with these, this is about the only one that has any numbers involved. In other words, the centroid. These relationships between these three lines are very interesting, that AO is exactly 2/3 of AD. And if you take a test on this chapter, a lot of questions will be involving that, because none of the other end centers have any mathematical relationship other than being equidistant from the vertices or equidistant from the edges of the triangle. That's the only other numerical aspect that you could be asked to deal with. Let me just look at this chapter should be a relatively quick one. Do deal with one other thing. Let's talk about it. The mid-segment of a triangle. If I take the midpoint of each side and connect those 3 points, I mean, the obvious is true. That side's equal to that side because it's the midpoint. That side's equal to that side because it's the midpoint. And that side's equal to that side because it's the midpoint. Now, let me draw some letters on here. A, B, C, D, E, F. It is true that line segment DE is parallel to AC. So DE is parallel to AC, and DE is equal to 1/2 of AC. And that might not be obvious. In fact, both of these things might not be obvious from constructing that triangle. In other words, making sure that that's the midpoint of AB, the midpoint of BC, and the midpoint of AC. that necessarily gives you a line that's parallel with your base and that's equal to 1/2 of your base.
Okay. Stuff we did on the last chapter, I think.
What's that?
This is stuff we kind of did the last chapter.
When you say the last chapter chapter was quadrilaterals, rectangles, squares, parallelograms,
We did a lot of
rhombus.
this, though.
What's that?
We did a lot of this, though.
Really?
Yeah, we did.
Well, I was trying to figure out why they skipped this chapter and went to the quads first.
Almost like they combined the chapters.
Yeah, it sounds like it.
As well.
Sounds like they did kind of combine the chapter. Another thing in this chapter, let's just talk about briefly, that's worth knowing, is that label the relationship between the angles. What's the smallest angle? What's the largest angle?
Smallest angle is C.
Okay.
Largest angle is B.
Yeah. In other words, the largest angle is always opposite the largest side. And the smallest angle is always opposite the smallest side. So if I were to give you that, and this angle was less than this angle, that would be impossible. Okay? So always remember that. And that also leads to, if you have this side equal to that side, then that angle has to equal that angle. In other words, isosceles triangles, that's why the opposite angles are equal. And if you have an equilateral triangle, where that's equal to that's equal to that, well then all three angles have to be equal. In fact, if all three are equal, they each have to be 60 degrees.
Mm-hmm.
Just look at this book. The measure of an exterior angle of a triangle is greater than the measure of either of the two non-adjacent interior angles. Well, this seems a little silly to me. Well, first of all, you have an exterior angle theorem that says what about 1, 2, and 3?
2 and 3 equal 1.
So now they're coming along and they're saying that there's an inequality theorem that says 1 has to be greater than 2 and it also has to be greater than 3. Well, I don't know why they have a separate theorem for that. It doesn't seem like they need one.
It's kind of blatant already, the fact that...
Yeah, it's implied by this because neither 2 nor 3 can be 0. So if neither 2 nor 3 can be 0 or negative, then 1 has to be greater than 2 and 1 has to be greater than 3. But in my book, that's theorem 5.12, exterior angle inequality. Well, I think we're going to be done with this chapter real quickly. We already did it once, and we've done it again today, and I think you get it. Yeah. All right. Well, let's be done with it. But this is what you covered today in class?
No, what we covered was like, I don't know, it was kind of continuation on from the end of break, and it's kind of like inequalities, cross multiplication with triangles. And
Similar triangles? Are you on to similar triangles yet?
yeah, similar triangles.
Ah, that's chapter 7 or 8. That's chapter 8.
It's chapter 6 in our book.
Oh. I thought that might be because you generally you skip from congruent triangles to similar triangles because they're very similar, you know. I mean, they're both the same shape. The only difference is that similar triangles are different sizes.
You don't need a third.
What's that?
The only difference in proving proving triangles are similar is you don't need the third.
Right, you just need angles. In other words, two equal angles means it's similar. You don't need any information about sides.
Mm-hmm.
Okay, well, that's good to know. All right. Well, we'll talk about similar triangles next Monday.
That sounds good.
All right, Cole. Have a good week.
You too.
Talk to you later. Bye-bye.